Each night, countless stars gaze down at you without a word. Researchers have established that our galaxy alone holds more planets than grains of sand on every shoreline on Earth. The numbers suggest the cosmos should be teeming with thinking, reasoning life. And yet, nothing. No transmission, no arrival, no evidence, just a quiet so profound it defies all expectation. Tonight, we examine every credible theory researchers have put forward to account for that quiet. From a galaxy-wide killing machine to civilizations cowering in dread, to the breathtaking notion that we are the very first minds to ever pose this question. If this haunts you at night, hit like and subscribe. Now, brace yourselves, we begin. The universe is roughly 13.8 billion years old. Across that vast sweep of time, stars ignited, worlds hardened, and the raw building blocks of life dispersed throughout hundreds of billions of galaxies. The reasoning is not complex. It powerfully implies that life should have taken hold countless times in countless locations, long before humanity ever drew breath. And yet, every instrument we turn toward the heavens delivers the same result: silence. This is the Fermi Paradox, named for physicist Enrico Fermi, who in 1950 posed a question so straightforward that it continues to unsettle researchers today. If the universe is this ancient and this expansive, and life chemistry seems this accessible, then where is everyone? Here is what makes this question genuinely disturbing. We are not merely talking about a missing transmission from some remote planet. We are confronting the complete, total absence of any traceable evidence of intelligence anywhere beyond Earth. No relic, no megastructure, no deliberate signal. A universe this immense, this old, and this chemically abundant should be bursting with signs. Instead, it appears barren. To grasp the gravity of that silence, consider scale for a moment. Our galaxy alone harbors somewhere between 200 billion and 400 billion stars. Astronomers have verified that most of them host planetary systems. A meaningful portion lie within what scientists term the habitable zone, where surface liquid water can persist. If even 1 in a million of those planets gave rise to intelligent life, our galaxy would contain hundreds of thousands of civilizations, many of them millions of years our elder. A civilization merely a million years ahead of us technologically would have had ample time to traverse every corner of this galaxy, repeatedly, even with capabilities only modestly beyond our own. The question is not just where the aliens are. The deeper question is why nothing at all has reached us. No probe, no transmission, no crafted object drifting through our solar system. That absence demands an explanation. Scientists have floated dozens over the decades. A few are comforting, most are not. They stretch from the notion that life is considerably rarer than we suppose, to the terrifying possibility that something routinely prevents civilizations from enduring long enough to make contact. Each explanation comes with its own implications for what our species might eventually face. Before we wade into those theories, it is worth sitting with the oddity of the problem itself. Every time humanity has conducted searches, we have deployed radio telescopes scanning specific frequencies, optical instruments hunting for laser bursts, and automated surveys logging strange stellar behavior. The searches have been limited, yes, but the silence has held firm. Some researchers contend our methods are too constrained, that we are scanning for one kind of signal in a cosmos that may communicate through means we have not conceived of yet. That is a reasonable critique, and it makes the problem more stubborn, not easier to set aside. What Fermi grasped in 1950 and what keeps researchers restless today is that the silence is not merely puzzling, It is almost statistically impossible to explain. The universe had every chance to fill itself with minds. Something prevented it. What that something is, and whether it lies in our past or still awaits us ahead, is the question that rewrites everything. Because the next theory we are about to explore does not simply describe the silence, it suggests that silence may be the most vital warning humanity has ever been handed. In 1960, astronomer Frank Drake stood before a chalkboard and composed an equation never intended to provide definitive answers. It was meant to structure our ignorance. The Drake equation mapped every factor needed to estimate how many communicating civilizations might exist in our galaxy at this moment. And when you work through it with honest eyes, it does something unexpected. It shows precisely where our certainty dissolves and where the unease begins. The equation chained several factors together. How many stars are born in our galaxy each year? How many host planets? How many of those planets sit in the habitable zone? Of those, how many develop life? Of those, how many develop intelligent life? How many construct technology capable of communication? And finally, for how long does that civilization persist and broadcast? The first few values are now fairly well established. Astronomers have confirmed through generations of observation that our galaxy produces roughly 1 to 3 new stars annually. Most have planetary systems. A significant fraction contain planets at the right distance for liquid water. These values, validated by the Kepler Space Telescope and its successors, suggest hundreds of millions of potentially habitable worlds in our galaxy alone. Then the equation encounters a wall. The moment it reaches the question of how many suitable planets actually produce life, scientific certainty dissolves. We have precisely one confirmed example of life in the universe: Earth. Every estimate beyond that is inference. Some astrobiologists believe life arises almost inevitably wherever conditions permit, because the underlying chemistry is so robust. Others argue that even on Earth, the leap from chemistry to a living cell may have been a near impossibility, demanding hundreds of millions of years and extraordinary fortune. That single unknown swings the final answer from millions of civilizations down to just one: us. We have no means yet to determine which estimate more closely reflects reality. But here is where things grow stranger. Even granting that life arises with relative ease, there is another variable in the equation that silently devours everything. And the final factor, the lifespan of a broadcasting civilization. How long does any technologically capable species endure before going dark? If civilizations typically survive only a few thousand years after reaching radio capability, roughly where humanity stands right now, the galaxy could be scattered with brief flames flickering on and off, never overlapping in time. Two civilizations might each endure 1,000 years, yet be divided by millions of years between them. They would never converge. They would never detect one another. This is called the temporal spacing problem, and it is one of the more quietly chilling responses to the Fermi Paradox. No dramatic extinction, no cosmic predator, just time, vast and indifferent, keeping every mind in the universe isolated. Drake himself ran the numbers at a 1960 conference and estimated roughly 10 communicating civilizations might exist in our galaxy. Modern estimates span from less than 1 to tens of millions, depending almost entirely on how optimistically you fill in the gaps. That range alone tells you everything. We are nowhere near resolving this. We are perched at the frontier of the unknown. And one of the bleakest explanations for why that equation keeps yielding low numbers involves something researchers call the Great Filter. The Great Filter is not a location. It is not something you can point to in space. It is a concept first articulated by economist Robin Hanson in 1998, and it may be the most disturbing idea ever expressed in clean logical terms. The premise is stark. If intelligent life is achievable, and the universe is old enough to have birthed it innumerable times, yet the galaxy appears empty, then something must be winnowing civilizations out before they achieve any widespread presence. Something blocks life from reaching the stars. The filter might be a single catastrophic barrier or a succession of smaller ones. It might operate at the level of chemistry, stopping life from initiating; at the level of biology, preventing complex cells from arising; at the level of cognition, blocking animals from developing technology; or at the level of civilization itself, preventing any species from surviving long enough to go interstellar. The terrifying aspect is not the filter's existence. It is the question of where it stands in relation to us. If the Great Filter lies behind humanity, we are extraordinarily fortunate. We already cleared the most punishing hurdle, the genesis of life, the evolution of complex cells, the emergence of intelligence. One of these transitions was so improbable that almost no other species in the galaxy made it through. We did. And if that holds, the path forward may be open. We could be among the exceedingly few minds in this galaxy, perhaps the only one, with a genuine future among the stars. But if the Great Filter lies ahead, the logic inverts completely. Every civilization that reaches our developmental level eventually encounters a wall it cannot survive: nuclear conflict, ecological ruin, artificial intelligence escaping its constraints, some technology not yet conceived turning against the species that built it. In that scenario, the universe's silence is not a mystery. It is a warning. Every civilization before us tried to cross this threshold and failed. We are drawing near to it now. There is a method for estimating which scenario is more probable, and the method will unsettle you. Discovering life elsewhere would normally feel like a triumph, but under the logic of the Great Filter, it would be a signal for alarm. If we find microbial life on Mars, or complex organisms in the subsurface oceans of a distant moon, or biosignatures in the atmosphere of an exoplanet, it means the emergence of life is not the filter. Life is common, which places the filter further down the path, closer to us, possibly still ahead. The more life we uncover in the cosmos, the grimmer our odds may become. This is established scientific reasoning. Though the filter itself remains theoretical, no physical law forbids civilizations from spreading. The absence of any evidence of civilizational expansion is real, documented, and without explanation. What we do know is this: the silence is real. The math insists on an explanation, and whatever is doing the filtering, it is thorough enough to have emptied an entire galaxy. The next question is whether that filter is a feature of the cosmos itself, or something older and more deliberate. The debate over whether the Great Filter lies behind or ahead of humanity is one of the weightiest in all of science. Two researchers can examine the same evidence and arrive at opposite conclusions, both logically sound, one leading toward hope, the other toward something close to dread. The argument for the filter being behind us hinges on a series of biological milestones that, in hindsight, seem absurdly unlikely. The first is the origin of life itself. For hundreds of millions of years after Earth formed, it was a barren rock. Life did not spring instantly from available chemistry. It demanded enormous spans of time and, by most reckonings, an extraordinary run of molecular fortune. The precise mechanism by which the first self-replicating molecule came into existence remains incompletely understood, a confirmed gap in scientific knowledge. Researchers still lack a complete model for abiogenesis, the process by which chemistry becomes biology. But even that may not be the hardest step. Roughly 2 billion years after simple bacteria appeared, something more improbable occurred. One bacterium was engulfed by another cell, and rather than being broken down, became a permanent internal component. That partnership generated the mitochondria. That event produced the complex cell, the foundation of all multicellular life. It appears to have occurred exactly once in 4 billion years of Earth history. Every plant, animal, and fungus alive today traces its lineage to that single improbable merger. If these events represent the filter, then we survived them, and the path ahead carries at least the possibility of being navigated. The argument for the filter lying ahead is harder to dismiss, and frankly harder to sit with. Look at the behavioral pattern of the only civilization we can observe, our own. Humanity achieved radio capability roughly 100 years ago. In that same span, we produced nuclear weapons capable of ending civilization, began reshaping the atmosphere in ways that destabilized the planet, and started building artificial intelligence systems whose long-term arc no one can reliably chart. We are, in the language of risk analysis, a species that acquires catastrophic capability faster than the wisdom to govern it. If this pattern holds universally, if every species that attains technological power does so before achieving the maturity to handle the consequences, then the filter ahead is not a cosmic accident. It is a developmental trap, a phase every species enters and most do not exit. A third possibility exists that few researchers discuss openly. The filter may not be a single event at all. It may be a sequence of compounding barriers, each one trimming the population of surviving civilizations until the number reaching interstellar scale rounds down to nothing. Under this model, no single step destroys everyone, but each step thins the field enough that by the time a civilization might be detected, statistically none remain. This stays theoretical, but it fits the available data. We stand at a specific place on this path. We have cleared the early hurdles, at least in part, and whether the hardest obstacles are already behind us, or whether we are approaching the most lethal threshold any civilization has ever encountered, we genuinely cannot say. What we do know is that the next theory presents a very different answer, one that requires no destruction whatsoever. In 1998, paleontologist Peter Ward and astronomer Donald Brownlee put forward something that cut against decades of optimistic thinking about life in the universe. Their argument was not that life is impossible elsewhere. It was that complex, multicellular, intelligent life demands such a precise combination of conditions that Earth may be genuinely extraordinary, not merely lucky, extraordinarily, almost impossibly lucky. The hypothesis opens with location. Earth does not sit just anywhere in the galaxy. It orbits within what astronomers designate the galactic habitable zone, distant enough from the radiation-drenched galactic core, but not so remote that the heavy elements necessary for rocky planets grow scarce. Stars closer to the center endure gamma-ray bursts and supernova shock waves at far greater rates. Stars near the outer fringes lack the chemical richness to construct complex worlds. Earth occupies a narrow band where conditions remain livable across billions of years. That is only the beginning. Our star is a steady, middle-aged star whose energy output has not changed dramatically in billions of years, granting life the time it needed to evolve. Many stars are more erratic, more violent, or too short-lived for complex biology to emerge. Earth's position within our system is equally remarkable. Our large companion moon exerts a gravitational influence that stabilizes Earth's axial tilt. Without it, our planet's axis would shift chaotically, triggering extreme climate oscillations that would almost certainly have prevented stable ecosystems from taking hold. Then there is Jupiter. The largest planet in our system acts as a gravitational buffer, capturing or redirecting a substantial fraction of the comets and asteroids that would otherwise strike Earth far more frequently. More impacts translate to more mass extinctions. More extinctions leave less time for complex life to stabilize and advance. Jupiter's presence may have been indispensable. Add plate tectonics that recycle carbon and moderate temperature across millions of years, a magnetic field deflecting lethal radiation, an oxygen atmosphere generated by early photosynthetic organisms, and the slender temperature range that preserved liquid water for billions of years. And the picture that emerges is not that of a typical world. It is a system of extraordinary precision where dozens of factors aligned in sequence. Ward and Brownlee reasoned that while simple microbial life might be widespread in the universe, the full arrangement of conditions required for complex life is so uncommon that Earth-like planets capable of producing intelligence might number in the dozens per galaxy, or fewer. This hypothesis remains contested. Some astrobiologists push back hard, arguing that life is adaptable enough to navigate around many of these constraints. But the rare earth argument holds its place as one of the most scientifically grounded answers to the Fermi Paradox. It requires no filter, no catastrophe, only the recognition that complexity is genuinely difficult to produce. If Ward and Brownlee are right, the silence carries a quiet explanation. Not that civilizations arise and collapse, but that the preconditions for intelligence were almost never satisfied in the first place. It is a lonely conclusion, though perhaps not the strangest on our list, because the next hypothesis does not suggest other civilizations never formed. It suggests they formed, flourished, and made a deliberate choice regarding us. In 1973, astronomer John Ball put forward something that sounds almost reassuring until you examine it long enough. His idea, known as the zoo hypothesis, proposes that intelligent civilizations do exist in the galaxy, advanced ones, possibly ancient ones, and that they are aware of our existence. They simply elect not to make contact. The rationale Ball offered mirrors what we do with wildlife preserves, or uncontacted communities. We observe, we study. We do not intervene, not because we are indifferent, but because we recognize that unrestricted contact destroys the very thing being observed. A civilization millions of years our senior that chose to monitor Earth would have compelling reasons to remain invisible. Consider what happens when a technologically superior culture encounters a less developed one. History gives a consistent answer. The less developed culture is overwhelmed. Its social frameworks collapse. Its belief systems fracture. Its sense of identity dissolves. An alien civilization wise enough to have survived for millions of years would understand this dynamic far better than we do. Non-interference may not be cruelty. It may be the most ethical response imaginable to encountering a young, fragile civilization. Under this hypothesis, the silence is not vacancy, it is management. An entire consortium of older civilizations may have agreed, formally or through deep cultural tradition, to leave developing species undisturbed until some threshold is crossed. That threshold might represent a certain level of technological achievement, a demonstrated capacity for global cooperation, or something we have not yet reached and cannot define from inside our current position. The zoo hypothesis is inherently resistant to testing. If a civilization is advanced enough to conceal itself from our instruments, we would have no means of detecting it. Every anomaly we attribute to natural causes could in principle be managed. The hypothesis endures precisely because it cannot be ruled out. But it invites an uncomfortable follow-up. If we are in a zoo, what happens when the exhibit evolves? In the past century, humanity has progressed from horse-drawn transport to nuclear arsenals to artificial intelligence to the threshold of interstellar communication. If a contact trigger exists, we may be approaching it faster than anything in our prior history would indicate. And the question of who determines when we are ready and what contact actually looks like when it arrives is one for which we have no framework at all. Some researchers extend the zoo hypothesis toward something slightly more ominous, not a preserve maintained out of compassion, but a quarantine upheld out of prudence. A civilization that has observed younger species destabilize their surrounding regions of space might contain emerging civilizations not for the newcomer's benefit, but for the protection of everyone else. In that version, the silence is not a gift, it is a fence. This remains speculative. No confirmed evidence exists of alien observation or management of Earth. But absence of evidence is not evidence of absence, especially when the entity concealing itself may be millions of years ahead of us in every domain. What we can say is that the zoo hypothesis, however unsettling, assumes something almost comforting, that advanced civilizations survive long enough to become prudent. The next theory assumes something altogether different. It assumes that in a galaxy packed with intelligent life, prudence is a luxury none of them could afford. The dark forest theory emerges from a thought experiment so bleak that it is difficult to hold. Popularized by Chinese science fiction author Liu Cixin, the underlying logic is not fiction. It is a game-theoretic argument about survival in a universe where resources are finite and intentions can never be verified. The argument rests on two premises. First, every civilization's paramount imperative is survival. Second, the universe does not contain sufficient resources for unlimited expansion by unlimited civilizations. From these two axioms alone, the theory arrives at a devastating conclusion. Imagine you are a civilization that has just detected a signal from another intelligent species. You know nothing about them beyond the fact that they exist and can transmit. You now face a decision. You could attempt contact and hope for cooperation, but their intentions cannot be confirmed. You have no way of knowing whether they are peaceful or predatory. If they are peaceful and you make contact, you gain a potential partner. If they are predatory and you make contact, you have just announced your location to something that may want to destroy you. If they are peaceful and you eliminate them preemptively, you lose one ally. But if they are predatory and you eliminate them preemptively, you survive. The mathematics of this scenario, given assumptions about resource scarcity and the impossibility of confirming intent across interstellar distances, push inexorably toward a single rational choice. Strike first, always. Under the dark forest model, the galaxy is not silent because life is scarce or civilizations are fragile. It is silent because every civilization that endures long enough to understand the stakes goes dark. Broadcasting your existence is not an invitation. It is a death sentence. Every star is a potential hunter. Every civilization is a creature moving through the dark, soundlessly, tracelessly, trusting nothing will notice. The implications for our own situation are disturbing. Humanity has been transmitting radio waves for over a century. Those signals have already traveled more than 100 light years, washing across thousands of stellar systems. If the dark forest model is accurate, we have already committed the most catastrophic possible blunder. More alarmingly, some researchers have proposed that we should immediately cease all broadcasting. The debate over whether humanity should send concentrated powerful signals toward distant star systems has grown genuinely divisive among scientists, largely because of arguments like this one. Stephen Hawking, before his death, issued a public warning against it. The dark forest theory is not confirmed science. It is a theoretical structure built on logical premises. Its weakest link is the assumption that cooperation is never rational. Some researchers argue that civilizations powerful enough to pose a threat would also be sophisticated enough to recognize that mutual cooperation generates better returns than mutual annihilation. But that argument presumes that rationality scales alongside technological capability, and history provides little evidence for that assumption. There is also a quieter variant of this idea that demands no malice at all, simply the recognition that contact between civilizations of vastly different capability levels is inherently destabilizing, and that advanced species may go silent not out of aggression, but out of careful, experienced caution. Either way, the universe goes dark. And if you believe the dark forest is the most disturbing answer on this list, what follows makes it look almost tranquil. Every civilization in human experience has eventually ended. Empires, cultures, city-states, languages, species. The rhythm of emergence, flourishing, and collapse runs so deep in both human and natural history that it barely registers as noteworthy anymore. But when you apply that rhythm to the Fermi Paradox, it stops being background and becomes the loudest signal of all. The self-destruction hypothesis holds that intelligent civilizations routinely eliminate themselves before making any meaningful contact with others, not through cosmic accidents, not through alien threats, but through their own inventions and their own choices. The timing is what makes this hypothesis impossible to shrug off. In the roughly 250,000 years that anatomically modern humans have existed, we spent nearly all of it in small, scattered groups, leaving negligible marks on the planet. Then, over the last 12,000 years, we built agriculture, cities, and organized societies. In the last few centuries, we built industry. In the last 100 years, we split the atom, altered the climate, and began building artificial intelligence systems that no individual fully comprehends or controls. The acceleration is the problem. With each passing century, humanity's capacity for accidental or deliberate catastrophe outpaces our capacity to govern it. Nuclear stockpiles exist today capable of ending complex life on Earth. Engineered pathogens are growing more accessible as biotechnology advances. Climate disruption is already reshaping the foundations that support modern civilization. And artificial intelligence is evolving along trajectories that its own architects describe as potentially beyond governance. These are not science fiction projections. They are confirmed, documented technological realities. The self-destruction hypothesis poses a straightforward question. If this pattern of accelerating capability paired with lagging wisdom is universal among intelligent species, how many civilizations successfully navigate the transition from planetary to interstellar? If the answer approaches zero, the galaxy fills with brief, radiant civilizations that consume themselves before sending a single probe beyond their home system. Researchers sometimes call this the critical phase, the interval between a civilization acquiring planet-scale destructive capability and either gaining the wisdom to manage it or the technology to escape the planet entirely. On Earth, that interval opened roughly in the middle of the 20th century and shows no sign of closing. How long it stays open before something catastrophic passes through it is a question no one can answer with assurance. What makes this especially pertinent to Fermi is the math. Even if 99 out of every 100 civilizations survive their critical phase, the galaxy would still harbor thousands of survivors. The silence would remain inexplicable. For this hypothesis to fully account for the emptiness, the survival rate would need to be extraordinarily low, perhaps approaching zero. And that, when you sit with it honestly, reflects back something about us right now in this century. We are not observing a civilization that failed in the past. We are living inside the critical phase. We are the experiment whose outcome has not been written yet. Some researchers find reassurance in the fact that we are still here, still talking, still scanning the sky. Evidence, they suggest, that something in our nature inclines toward survival. Others are not so sanguine. What follows does not wait for civilizations to destroy themselves. It proposes that something in the galaxy takes a far more deliberate approach. The berserker hypothesis is not a metaphor. It is a specific logical proposition about what a sufficiently advanced civilization might do to protect its long-term dominance. Once you follow the reasoning, it is very difficult to stop thinking about it. The concept entered science fiction through Fred Saberhagen's work, but its underlying logic has been taken seriously by researchers in astrobiology and existential risk. The hypothesis proposes that at some point in galactic history, one or more civilizations constructed self-replicating autonomous probes carrying a single directive: destroy any other civilization encountered before it can become a competitor. To understand why a civilization might pursue such a strategy, you must think in long time scales. A civilization that endures tens of millions of years eventually confronts a problem. Other civilizations, if permitted to develop, will eventually achieve comparable capability. At that point, the older civilization's advantage is no longer assured. The strategically rational move is to eliminate rivals early, before they become dangerous. Rather than waiting for a confrontation between equals, self-replicating probes solve the problem of scale. You do not need a fleet of vessels to patrol the entire galaxy. You build one probe capable of mining raw materials from asteroids, constructing copies of itself, and dispersing. Over millions of years, a single original probe multiplies into trillions, advancing through the galaxy like a patient, methodical tide. Any world showing signs of technological development gets flagged, then erased. Under this model, the universe's silence carries a simple explanation. We have not yet been found. Or perhaps we have, and the countdown has already begun. That second possibility is not a comfortable one to sit with. No confirmed evidence exists for berserker probes, no detected artifacts, no observed destruction events that cleanly fit the profile. But the difficulty is this: if the probes are designed for stealth, we might not recognize them. If they are patient, they may wait until a civilization crosses some specific threshold of development before acting. We would receive no warning. Some researchers have noted that Oumuamua, the enigmatic interstellar object that passed through our solar system in 2017, could theoretically fit the profile of a probe. This is not the scientific consensus, which leans strongly toward natural explanations, but the object behaved in ways that defied every known natural model, and the question remained open longer than most anomalies ever do. The berserker hypothesis also offers a grim lens through which to examine a pattern in the astronomical record. Several of the most promising nearby star systems for hosting life-bearing planets appear to have undergone significant disruption events in their past. The causes remain debated. What gives the berserker concept its lasting power is not any individual piece of evidence. It is the logical coherence of the premise. In a universe where competition for survival is real and technological capability escalates without limit, preemptive elimination is a defensible long-term strategy. It is horrifying precisely because it makes sense. The galaxy may not be silent because life is rare or fragile. It may be silent because something already swept through and made it that way. And if that is even partly true, the most important question facing humanity is not how to locate other civilizations. It is whether locating them would be the last act we ever perform. But here is what no one anticipates. The next theory requires no destruction at all. It requires only speed, and it rewrites the entire timeline. In 2020, a team of astrophysicists, including Robin Hansen, introduced a model that reframes the Fermi Paradox in a way that cuts through most of the speculation. Their framework, called the Grabby Aliens model, begins from a single premise. When civilizations reach a sufficient level of technological capability, they expand rapidly and permanently. The model does not assume hostility. It does not require self-replication or elimination. It simply assumes that a technologically advanced civilization, given sufficient time, will expand outward through space at a meaningful fraction of light speed, colonizing stellar systems and leaving behind a visible, growing boundary of transformed space. The critical insight lies in what this implies about timing. If such civilizations had existed and begun expanding even 1 billion years ago, their advancing frontiers would already have reached us. The galaxy is old enough, and the physics of expansion at even a modest fraction of light speed is rapid enough, that any civilization with a meaningful head start would have arrived by now, not via radio signal, but by physically showing up. The fact that we have not been absorbed, contacted, or even grazed by the expanding edge of any such civilization is itself meaningful data. Under the Grabby Aliens model, this points to one of two conclusions. Either no such civilizations exist because something prevents them from reaching the expansion stage, or they exist but have not started yet, meaning we sit very close in cosmic time to when the first Grabby civilizations will emerge, and we might be one of them. This second possibility carries a striking implication. If such civilizations are rare but inevitable, and if we are near in cosmic time to when the first ones appear, then humanity may be among the earliest species ever to approach this threshold. We are not late arrivals. We are extraordinarily early. The model projects that if you observed the universe 1 billion years hence, assuming humanity or its successors had expanded, you might see the cosmos filling with competing spheres of influence from multiple originating points, each expanding outward at fractions of light speed, eventually meeting at boundaries and arriving at some form of equilibrium or confrontation. Right now, the universe appears vacant, because the era of expansion has not yet begun. The window of silence we observe may be temporary, a cosmic dawn before a very loud day. The Grabby Aliens model has passed peer review and earned genuine academic respect. It does not resolve every dimension of the Fermi Paradox, but it provides a mathematically coherent answer to the timing question. We detect no expanding civilizations because the expansion era is only just getting underway. Whether this is reassuring or alarming hinges on perspective. On one hand, we may simply be first, not isolated in a hostile universe. On the other, If we are among the earliest grabby civilizations to emerge, then the choices we make in this century, how we expand, what we consume, how we treat the life we encounter, will set precedents echoing across billions of years of cosmic history. That is not a modest responsibility. But not everyone believes the Fermi Paradox is answered by anything written in the stars. Some think the answer might be encoded in the very fabric of reality. And the next theory is arguably the strangest of all. The simulation argument was formally developed by philosopher Nick Bostrom in 2003 and is worth understanding on its own terms before connecting it to the Fermi Paradox. Bostrom's argument does not assert that we are simulated. It presents a trilemma. One of three propositions must be true. Either almost all civilizations at our level of development go extinct before acquiring the ability to run detailed simulations of conscious minds, or almost all technologically mature civilizations choose not to run such simulations, or we are almost certainly living inside a simulation right now. The logic is clean. If even one civilization in the universe's history survived long enough and chose to run detailed mind simulations, it could run an astronomically vast number of them. The simulated minds would vastly outnumber the genuine ones. Therefore, any randomly selected mind, including yours, is statistically far more likely to be simulated than real. Now connect this to Fermi. If we inhabit a simulation, the universe's silence has a trivial explanation. The sky is empty because the programmer never populated it. No other civilizations are transmitting because none were rendered with enough resolution to transmit. The universe extends only as far as its observers demand. Beyond the reach of our instruments, there may simply be nothing, not empty space, but the absence of code. Yes, this is not a scientific hypothesis in the conventional sense. It cannot currently be tested, but it is not pure philosophy either. Multiple physicists have proposed theoretical experiments capable of detecting signatures of discretized spacetime, the kind of artifact expected if physical reality were built on a computational lattice rather than continuous mathematics. Those experiments have not returned conclusive results. The question remains open. From a Fermi perspective, the simulation answer is simultaneously the cleanest and the most structurally vertiginous. It requires no great filter, no self-destruction, no alien hunters, only a willingness to accept the possibility of a layer of reality beyond what we can examine, and that whoever administers that layer chose not to include other voices in our rendering of the cosmos. Some physicists counter that simulating a universe with the physical resolution we observe would require computational resources that may be beyond even an arbitrarily advanced civilization. It is a fair objection, but not a definitive refutation. We do not know the computational limits of something operating outside the constraints of our physics. What makes this theory resonant in the context of Fermi is its explanatory economy. The silence is not a puzzle to solve. It is a design decision. And if it is a design decision, the question shifts entirely. Not where is everyone, but why were we built to feel alone? That question has no scientific answer yet, but it carries a quality that sets it apart from most Fermi solutions. It makes the silence feel purposeful, curated, intentional. Whether that possibility comforts or disturbs you likely reflects something about you rather than about the universe. What we turn to next is not philosophy. It is hard biology, and it may be the most grounded, most sobering entry on this entire list. For most of the 20th century, astrobiology operated on a largely unexamined premise, that once life begins, it tends to grow more complex over time. Simple organisms become multicellular. Multicellular organisms develop nervous systems. Nervous systems generate brains. The story seemed to carry its own momentum, and Earth was simply one of billions of planets riding that escalator. That assumption has been quietly dismantled over the past 2 decades, not by any single dramatic finding, but through the accumulated weight of detail about just how contingent and precarious the path from simple to complex actually was on Earth. Consider the timeline. Life appeared on Earth within a few 100 million years of the planet forming, geologically fast, suggesting that the origin of simple life may not be the primary barrier. For roughly 3 billion years after that, single-celled organisms dominated. 3 billion years of chemistry, evolution, and environmental pressure, and life advanced nowhere structurally. Then the eukaryotic cell appeared. This is the cell type underlying every complex organism alive today, every plant, every animal, every fungus. As discussed earlier, it arose from one extraordinary symbiotic event in which one cell engulfed another and, instead of breaking it down, retained it as a permanent internal structure. Scientists believe this happened exactly once across 4 billion years of Earth history. Once, no evidence that it has occurred anywhere else. After the eukaryote appeared, another billion years elapsed before multicellular life became widespread. Then came the Cambrian explosion, the geologically rapid emergence of most major animal body plans, apparently triggered by atmospheric oxygen crossing a critical threshold. Not a gradual ascent, but a threshold event. Each of these transitions required its own specific precondition. The chemistry had to be right. The environment had to hold stable long enough. The necessary mutation had to occur at precisely the right moment in precisely the right organism. Miss any single one, and the escalator stops. You get a world of bacteria indefinitely. Researcher Andrew Knoll of Harvard has spent decades studying early Earth life and argues consistently that the emergence of complexity was neither inevitable nor foreseeable. It was a cascade of accidents, each one essential for the next. This is not pessimism from a scientific standpoint. It is an honest accounting of the fossil and molecular record. If this reading is correct, the universe is probably not devoid of life. It is probably dense with bacteria, simple organisms thriving in oceans beneath ice crusts and in warm subsurface rock across thousands of worlds. But the transition to complexity, to nervous systems, to brains, to language and technology, may have occurred only a handful of times in the entire observable universe. Simple life, likely common, confirmed possible on at least one world. Complex life, possibly the rarest phenomenon in existence. The silence overhead is not because the universe is dead. It is because complexity is a near impossible accident that happened to us, and to almost nothing else. If that is true, the stakes of our survival just increased by several orders of magnitude, because what we consider next is the possibility that not only is complex life rare, but that intelligent technological life may have occurred exactly once. Here with us, there is a version of the Fermi solution that demands no catastrophe, no filter, no alien hunters, and no simulation. It requires only a specific reading of probability combined with the known age and composition of the universe. Its conclusion is this: we may be the first intelligent civilization ever to exist, anywhere. The idea does not rest on arrogance. It rests on timing. The universe is 13.8 billion years old. For roughly the first 9 billion of those years, the conditions for complex rocky planets like Earth were not reliably in place. The earliest generations of stars contained almost no heavy elements. They burned brilliantly and died quickly, seeding the cosmos with carbon, oxygen, iron, and the other atoms that chemistry and biology require. Only after multiple cycles of stellar birth and death did enough of those elements accumulate to construct the kind of world Earth represents. Our planet formed around 4 billion years ago. Complex life took more than 3 billion years to appear. Technological intelligence required several 100 million years beyond that. And when you place humanity on the timeline of cosmic chemical enrichment, we appear at almost the earliest possible moment that beings like us could have emerged. Not billions of years late to a packed gathering, but right at the opening. If intelligence demands the heavy element richness that only became widespread roughly 5 to 8 billion years ago, and if intelligence also requires several billion years of biological evolution, then there is a narrow window at the very front edge of possibility where the first minds could arise. We may be sitting in that window right now. Under this framing, the universe is simply not yet old enough to be full of intelligence. We are not survivors of a galactic purge. We are not overlooked by some wiser civilization. We are simply early, the first species, or among the very first, in a universe only now reaching the point where such crossings become possible. The implications are immense. If we are first, everything that follows is a blank page. There is no elder civilization to learn from, no precedent to follow, no cautionary tale from a predecessor who already made the catastrophic mistakes. We leave the first footprints in what may eventually become a cosmos, dense with intelligence, but only if we survive to hand something forward. This is not a confirmed conclusion. It is a theoretical possibility consistent with current cosmological data. Researchers like David Kipping at Columbia University have published work suggesting that the distribution of intelligence emergence times across the universe may genuinely favor very early emergence for the first civilization, placing us at or near that leading edge. The loneliness implied by this hypothesis differs from that in other Fermi solutions. It is not the loneliness of the last survivor. It is the loneliness of the first arrival, a universe teeming with unrealized potential, none of it yet awakened, and us standing at the beginning of something that has never occurred before. There is weight in that. If we are first, the survival of Earth's civilization is not merely our concern. It is the only thread connecting this universe to the possibility of a future populated by minds. And if that is not enough to hold in your thoughts, the next section introduces something suggesting that our entire search strategy may itself be the problems. The search for extraterrestrial intelligence has been driven for decades by a single approach: radio telescopes aimed at selected frequencies, listening for structured signals that natural processes would not generate. This formally began in 1960 with Project Ozma and has continued through various programs ever since. It is logical, it is scientifically defensible, and it may be missing the point entirely. Here is the difficulty. Radio waves disperse as they travel. The energy spreads across an ever-widening sphere of space. By the time a signal has crossed a few hundred light years, it has thinned to a level extraordinarily difficult to separate from the cosmos's background static. Our own most powerful deliberate broadcast, the Arecibo message, sent in 1974, would be effectively undetectable by our current technology at even a fraction of the distance to the nearest stars. This means that even if hundreds of civilizations were transmitting using technology equivalent to ours, we would almost certainly fail to detect them across interstellar distances. Radio is not a practical interstellar communication medium for civilizations at our level of development. and civilizations substantially more advanced may have long since abandoned it. Consider humanity's own trajectory. We have been broadcasting powerful omnidirectional radio signals for roughly a century. But the direction of communication technology is already shifting away from wide dispersion, high power transmission, and toward tightly focused, encrypted digital channels. Powerful broadcast signals are yielding to fiber optics and point-to-point links. As a civilization's communication infrastructure matures, it tends to grow quieter and harder to detect from the outside. An advanced civilization might be essentially invisible to radio-based searches, not because it stopped communicating, but because it transitioned to methods we have not yet developed. Tightly focused laser pulses, neutrino-based transmissions, gravitational wave modulation, any of these would pass straight through our current instruments without leaving a recognizable trace. What researchers increasingly advocate is a pivot toward what they term technosignatures, evidence of technology that persists and scales beyond what any individual broadcast could offer. Thermal signatures from industrialized worlds. Atmospheric chemistry inconsistent with any purely natural model. Structured light curves from stars with artificial objects in orbit. These markers would be harder to conceal and would not require a civilization to be actively attempting communication. The logic is compelling. If you want to find a city, you do not monitor for telephone calls. You look for lights from altitude. Our current search strategy is the equivalent of listening for phone calls across an ocean, while the city we seek stopped using phones a century ago. The silence we receive may have nothing to do with absence. It may have everything to do with the limitations of our instruments and the assumptions embedded in our methods. This is an area of active, ongoing scientific discussion, not a fringe argument. It sits at the center of current astrobiology research and is increasingly shaping how funding bodies direct their resources. And, speaking of things we may have already encountered without recognizing, the following section concerns one of the most celebrated anomalies in this entire field, a signal that appeared once, lasted 72 seconds, and remains unexplained to this day. If a civilization advanced enough to construct structures visible from across the galaxy truly existed, it would almost certainly not announce itself through a radio broadcast. It would announce itself by reshaping its environment on a scale so vast that the evidence would be embedded in starlight, detectable by any civilization patient enough to look. This is the logic underlying the study of technosignatures, the search for physical evidence of technology rather than deliberate communication. And the central object of that search is the Dyson sphere. Physicist Freeman Dyson proposed in 1960 that a civilization confronting energy constraints would eventually identify the most accessible available power source, the total output of its star. A sufficiently advanced civilization would build a structure, not necessarily a rigid shell, but perhaps a swarm of orbiting collectors and habitats, that captures a substantial portion of its star's radiation. Viewed from outside, a star encircled by such a swarm would appear anomalous. It would radiate less visible light than expected for its mass and type, while emitting excess energy in the infrared. That specific signature, anomalously low visible output paired with anomalously elevated infrared emission, is detectable by our instruments across thousands of light years. Astronomers have cataloged candidates. None have been confirmed as artificial, but systematic searches have only recently become feasible. The Gaia mission, the Wide Field Infrared Survey Explorer, and forthcoming missions like the Nancy Grace Roman Space Telescope are producing stellar catalogs at scales that make systematic technosignature searches possible for the first time. Researchers are now using machine learning to flag stars behaving in ways inconsistent with known natural models, scanning for irregular and structured dimming patterns that an incomplete or partially constructed megastructure might produce. Beyond Dyson spheres, researchers are examining other engineering signatures. Stars losing mass in non-standard patterns might be hosting planetary-scale mining operations. Planetary systems with unusual orbital architecture might have been deliberately reorganized. Gas giants, stripped of their outer layers, might carry the marks of civilizational-scale resource extraction. None have been confirmed, but the scientific community increasingly regards technosignature research as a legitimate and necessary element of any serious search for extraterrestrial intelligence. NASA formally funded technosignature research beginning in 2019, a significant institutional shift. One particular class of technosignature has attracted enormous scientific attention: starlight that dims in irregular, non-periodic patterns. Not the clean, repeating transit signature of an orbiting planet or the predictable curve of a binary companion, but complex fluctuations varying in depth, duration, and shape from one event to the next. This pattern is not consistent with any known natural object's behavior, and it has been detected around a real star. That star sits roughly 1,500 light-years away. Its behavior has generated more peer-reviewed papers, more competing hypotheses, and more genuine scientific controversy than almost any other single object in the past decade. What is happening around that star, and why scientists still cannot reach consensus on a natural explanation after years of intensive observation, is the subject of the next section. The longer you examine the data, the harder it is to feel settled. On August 15, 1977, a radio telescope at Ohio State University detected something anomalous. The instrument was part of a program called Big Ear, one of the earliest organized searches for extraterrestrial radio transmissions. It swept the sky automatically, printing rows of encoded data onto continuous paper. A volunteer named Jerry Amon was reviewing the printouts days later when he noticed a sequence of numbers and letters that stood in stark contrast to everything surrounding it. The signal persisted for exactly 72 seconds, the full duration the telescope's field of view could track any fixed point in the sky. It appeared to originate from the direction of the constellation Sagittarius. Its intensity, frequency, and narrowband structure matched precisely what researchers had theoretically predicted an artificial extraterrestrial signal would look like. Amon circled the sequence and wrote one word in the margin: "Wow, the signal has never been detected again." Dozens of follow-up observations have targeted the same region using more powerful instruments over the nearly 50 years since. Nothing has returned. No repetition, no faint echo, no corroborating detection from any other instrument during the same window. Whatever produced it either appeared once, moved on, or ceased. This is confirmed observational data. The signal is real. Its characteristics are genuinely anomalous. What generated it is entirely unknown. Over the decades, several natural explanations have been advanced. A comet releasing hydrogen gas in a focused direction was among the more recent candidates, proposed by astronomer Antonio Paris in 2017. His hypothesis attracted significant attention and equally significant skepticism. Multiple researchers examined his analysis and concluded that the comets he identified would not have been correctly positioned to produce the observed signal, and that a hydrogen gas explanation failed to adequately account for its narrowband character. The comet hypothesis is not accepted as definitive by the broader scientific community. The WOW signal occupies a rare and uncomfortable niche. an anomaly with no confirmed natural explanation, but also no confirmed artificial one. It is not proof of extraterrestrial intelligence. It is an unexplained data point, and science must operate honestly within that distinction. What makes it particularly striking is the frequency. The signal appeared near 1420 megahertz, the emission frequency of neutral hydrogen, the most abundant element in the universe. Long before the detection, researchers had proposed this frequency as a logical choice for any civilization attempting interstellar contact, a universal landmark recognizable to any species that had studied the cosmos. The wow signal appeared there precisely. Whether that is an extraordinary coincidence or something more significant, science cannot currently determine. What it can say is that nearly 50 years of follow-up observation have not produced a satisfying natural explanation. That absence is not evidence of extraterrestrial origin, but it is evidence that we encountered something our models have not fully accounted for. One observation, one margin notation, nearly 50 years of silence from the same patch of sky. If the wow signal was the most celebrated single anomaly of the last century, the next one arrived more recently, unfolded over years rather than seconds, and generated a level of scientific bewilderment the field had not experienced in decades. N. 2015. A paper by astronomer Tabetha Boyajian and a team of collaborators described a star roughly 1,400 light-years away that was doing something no natural model could cleanly explain. The star, formerly catalogued as KIC 846, 2852 but now almost universally known as Tabby's star, was dimming, not in the regular periodic pattern of a transiting planet, and not in the smooth, predictable arc of a binary companion. It was dimming in complex, irregular bursts, sometimes by as much as 22% over a matter of days, then brightening, then dimming again in an entirely different pattern. 22% is an enormous dimming event for any star. A Jupiter-sized planet, among the largest natural objects capable of transiting a star, blocks roughly 1% of stellar light. Whatever was partially eclipsing Tabby's star was, by any natural measure, implausibly large, and it was neither regular nor symmetric, nor consistent with any known type of orbiting body. The data came from the Kepler Space Telescope, which simultaneously monitored over 150,000 stars for planetary transits. Across 4 years of continuous observation, Tabby's star produced the most anomalous light curve in the entire dataset. Citizen scientists participating in the Planet Hunters project flagged it as something they had never encountered before. Their instinct was correct. Naturally, researchers initially explored the most striking explanation. The irregular dimming pattern maps well onto what you would expect from a Dyson swarm. A collection of large orbiting structures at various stages of assembly, blocking differing amounts of light as components move through the line of sight. This was not fringe speculation. It appeared in peer-reviewed publications and was taken seriously by multiple researchers. The scientific community did not converge on that explanation. This is confirmed. After years of intensive observation, the most widely accepted hypothesis today is that a cloud of disintegrating dust and debris, possibly the remnants of a fragmented comet family or a shattered planetesimal belt, is responsible for the irregular dimming. But that explanation carries its own unresolved difficulties. The scale and structure of the dimming events remain hard to fully account for with available natural models. More recently, astronomers found that Tabby's star also shows a long-term, gradual dimming trend extending across years, a slow reduction in overall brightness entirely separate from the sharp transit events. This long-term behavior is also anomalous and adds another layer of complexity to any proposed natural explanation. Tabitha Boyajian herself has been measured and careful in her public statements, consistently maintaining that the most probable explanation is natural, and that no evidence of artificial construction has been confirmed. That scientific caution is appropriate, but she has also consistently acknowledged that the object remains without a complete explanation. What makes Tabby's star significant in the context of the Fermi Paradox is not any specific claim about its nature, it is what the object represents methodologically. For the first time, astronomers identified a real stellar system exhibiting behavior that, without any bias toward dramatic conclusions, a techno-signature researcher would have flagged as a candidate warranting serious investigation. The instruments functioned, the anomaly was real, the natural explanation remained incomplete. That is not a discovery of alien technology, but it is proof that searching this way might actually yield something. And, if Tabby's star left researchers unsettled, the next anomaly did something far stranger still. It did not sit in a distant system dimming passively. It traveled through our own solar system. It moved, and it refused to behave like anything ever previously catalogued. In 2007, astronomers reviewing archival data from the Parkes Radio Telescope in Australia encountered something that should not have been there. A burst of radio energy lasting only a few milliseconds, with an intensity so extreme it had to have originated from beyond our galaxy. The burst was so brief, so powerful, and so structurally unusual that researchers spent years confirming it was not instrument error before publishing. It was not instrument error, and it was not alone. Since that first detection, astronomers have catalogued hundreds of fast radio bursts, brief flashes of radio energy lasting anywhere from a fraction of a millisecond to several seconds. Each releases more energy in that instant than our sun emits over several days. They arrive from random directions across the sky, suggesting sources distributed throughout the universe, rather than concentrated in any particular region. Then, their precise physical origin was for years entirely unknown. What deepened the mystery was repetition. Most fast radio bursts appeared once and never returned. Then researchers identified a small subset that repeated, sometimes irregularly, sometimes in structured cycles. One source, catalogued as FRB 121102, has been observed to recur in clusters that appear periodically, then fall quiet, then cluster again. The cycle runs approximately 157 days. Regular enough to suggest an underlying mechanism, irregular enough to resist simple explanation. The leading scientific explanation today centers on magnetars, neutron stars with extraordinarily powerful magnetic fields, among the most extreme environments in the known universe. A magnetar can release vast amounts of electromagnetic energy during starquake events, when stresses on its rigid crust produce sudden fractures. In 2002, astronomers detected a fast radio burst from a magnetar within our own galaxy, the first time such an event was confirmed to originate from a known source. It was a significant milestone, demonstrating that magnetars can produce at least some fast radio bursts. But it did not close every open question. The energy levels of some observed bursts, particularly those originating from distant galaxies, exceed what current magnetar models predict under standard physics. The structured periodicity of repeating sources remains incompletely explained. The sheer variety in burst characteristics across the catalog suggests a single source type may not account for everything. Some researchers have explored whether a subset of fast radio bursts could constitute technosignatures. The energy required to produce a burst at the intensities we detect from extragalactic distances is so enormous that if it were artificial, the engineering would dwarf anything conceivable today. Physicist Avi Loeb of Harvard has proposed that a sufficiently powerful artificial emitter designed for interstellar propulsion rather than communication could theoretically produce a fast radio burst as a byproduct, what he terms the lighthouse model. This is not the scientific consensus. It is a theoretical possibility raised by a credentialed researcher that has not been ruled out. What fast radio bursts confirm, regardless of origin, is that the universe contains physical processes producing structured, energetic emissions on timescales, and at intensities we are only beginning to characterize. Every time we have opened a new observational window onto the cosmos, we have encountered the unexpected. Fast radio bursts were invisible to us until 2 decades ago. What else remains currently invisible? But compared to what entered our solar system in 2017, fast radio bursts feel safely remote. What came next did not stay at a polite extragalactic distance. It came directly to us. On October 19, 2017, an astronomer at the Haleakala Observatory in Hawaii detected a fast-moving object passing through our solar system. Initial calculations suggested an ordinary comet from within our own planetary neighborhood. Closer analysis stopped the field cold. The object had originated from outside the solar system entirely. It was the first confirmed interstellar visitor ever detected. They named it Oumuamua, a Hawaiian word meaning roughly a scout or messenger from far away arriving first. Initially, astronomers anticipated a routine classification, an interstellar rock or icy body ejected from some distant system and drifting through space for millions of years before a chance gravitational encounter sent it through ours. The universe is ancient. Ejected debris should be common. Detecting one passing through seemed surprising but scientifically manageable. Then the data arrived, and manageable became the wrong word. Oumuamua's shape was unlike any previously catalogued natural object. Estimates based on its reflectivity and brightness variation suggested extreme elongation, a length-to-width ratio of perhaps 10 to 1 or more. No known natural formation process reliably produces objects with that geometry at that scale. Comets are irregular but not blade-like. Asteroids vary, but not that dramatically. The geometry alone was anomalous. Then came the trajectory problem. As Oumuamua departed our star, it accelerated, not dramatically, but measurably and persistently beyond what gravity alone could account for. Comets accelerate in this fashion when solar heat vaporizes subsurface ice, generating outgassing jets that push the object. This is well understood. Astronomers searched for evidence of outgassing. They found none. No detectable gas cloud, no dust trail, no coma, just clean, unexplained acceleration. Every proposed natural explanation for the anomalous trajectory has been published and challenged. One hypothesis suggested it was composed of hydrogen ice, which would outgas invisibly. The difficulty: hydrogen ice is unstable in the interstellar environment across the travel time implied by its trajectory. Another suggested it was a thin, flat piece of natural material propelled by radiation pressure from our star, like a natural solar sail. The difficulty: an object thin enough to be accelerated that way by light would need to be no more than a millimeter thick across a surface hundreds of meters wide, a geometry with no known natural formation mechanism. Avi Loeb of Harvard, one of the most prominent astrophysicists in the field, argued publicly and in a published book that the most parsimonious explanation for Oumuamua's combined properties was that it was artificial. Not certainly artificial, but that given the anomalies, the hypothesis warranted serious scientific examination rather than reflexive rejection. The mainstream scientific community pushed back, largely maintaining that a natural explanation would eventually surface. In 2023, researchers proposed a new mechanism involving nitrogen ice fragments from a disrupted exoplanet surface, which could theoretically produce the observed properties. That explanation received attention but has not achieved universal acceptance. What Oumuamua confirmed, regardless of its origin, is that interstellar objects pass through our solar system, and that at least one of them behaved in ways our models failed to predict. A second interstellar visitor, Borisov, arrived in 2019 and behaved precisely as expected, like a perfectly ordinary comet. The contrast only deepened the strangeness of the first. The story of Oumuamua is not closed. The object is long gone, too distant now for any instrument to reach or examine. Whatever it was, it passed through and left us with questions we still cannot resolve. And if something from outside our solar system could arrive without warning and depart without explanation, it forces a harder reckoning. What else might be out there that we are not equipped to recognize? One of the quieter responses to the Fermi Paradox requires no rare civilizations, no self-inflicted catastrophes, no concealment. It demands only that the universe is structured in ways that make crossing it physically prohibitive for any civilization, regardless of how advanced. And the more carefully you examine the physics, the harder it is to set aside. The first obstacle is energy. Accelerating a spacecraft to even 1/10 of light speed, the minimum velocity considered relevant for practical interstellar travel within a human lifespan, demands energy expenditures that dwarf anything our civilization currently produces. For a vehicle of modest mass, the energy required approaches what thousands of simultaneous nuclear detonations would generate, just to reach that fraction of light speed. Scale the vehicle upward, add life support, fuel reserves, and shielding, and the energy demands grow overwhelming. Then there is the fuel dilemma. Any rocket-based system must carry its own propellant, but propellant has mass. More mass requires more propellant to accelerate it. The relationship is exponential, not linear. As mission distances grow, the required fuel mass rapidly becomes absurd. Chemical rockets are obviously inadequate. Nuclear propulsion helps but falls short. Fusion drives, if achieved, would improve the situation significantly. But even under optimistic fusion projections, the engineering required for a basic interstellar mission represents centuries of advancement beyond our present capability. The second barrier is time. Even at 1/10 of light speed, the voyage to the nearest confirmed stellar system, Proxima Centauri, takes approximately 40 years. The nearest systems, plausibly hosting Earth-like worlds, are farther still. For a civilization attempting to survey a galaxy 200,000 light-years across, the timescales are nearly impossible to internalize. Sending probes at even significant fractions of light speed across the full galactic breadth would take millions of years. Civilizations waiting for those probes to return or their colonies to report back would require institutional continuity across spans exceeding the entire recorded history of human civilization, thousands of times over. The third barrier is collision risk. At high velocities, interstellar space is not truly empty. Dust grains and microscopic particles, invisible and essentially undetectable at interstellar distances, become lethal at relativistic speeds. A particle no larger than a sand grain encountered at a substantial fraction of light speed carries the kinetic energy of a small explosive charge. Shielding against such impacts across decades-long journeys is an engineering problem with no current solution. These barriers are real. They are grounded in established physics. They do not yield to optimism or creative framing. What they imply for the Fermi Paradox is that even civilizations far more advanced than us may have concluded that physical interstellar travel is simply not viable as a general approach. The galaxy may harbor intelligent species that have never left their home systems, not because they lack the will or the curiosity, but because the physics will not cooperate. In that case, the silence is not an indication of absence. It is an indication of confinement. Each civilization isolated within its own small sphere, perhaps listening, perhaps transmitting, but unable to bridge the gulfs between them. If that confinement is real and universal, the next question grows stranger still. Could a civilization leave a detectable imprint without physically traveling? And might any such imprints already exist, waiting to be read? Most discussions of the Fermi Paradox frame it as a spatial question. Where are they? Why have they not come here? But there is an equally powerful formulation of the same problem that operates entirely in time, and it may be more disquieting than any spatial argument. The universe is 13.8 billion years old. Complex life on Earth required roughly 4 billion years to produce intelligence, if intelligence is even somewhat probable given the right conditions. And if those conditions existed elsewhere in the galaxy several billion years before they existed here, then civilizations may have arisen, peaked, and ended billions of years before a single human ancestor stood upright. A civilization that reached its apex 2 billion years ago would emit no radio signals detectable today. Its broadcasts, if they ever crossed our region of space, passed through billions of years ago, when the only life on Earth was single-celled organisms with no instruments and no awareness. Any physical artifacts it launched into space would by now be indistinguishable from natural debris, redistributed and eroded by billions of years of cosmic process. The inverse holds equally. Civilizations that will emerge in the future, millions or billions of years from now, as stellar conditions evolve further, will arrive long after we are gone. From their vantage, we will be the ancient and silent ones. Our transmissions will have faded to nothing, and our artifacts, if any persist, will be incomprehensible remnants. This is sometimes called the temporal communication problem. Two civilizations can share the same galaxy and yet be so separated in time that they never have any opportunity to sense each other's existence. The overlap required for detection is not merely proximity in space. It is proximity in time. On cosmic scales, that is a far narrower window. Astronomer Milan Cherkovich has written extensively on this idea, arguing that SETI is built on an implicit assumption that other civilizations exist on timescales similar to ours. If civilizations can persist for millions or billions of years, the galaxy's history of intelligence may reside primarily in its past, not its present. We may be searching for something that flourished and vanished long before our instruments existed. There is also a forward-facing version of this argument with its own disturbing implication. If intelligence is genuinely rare, and we are among the first, then the full blossoming of minds in this universe may lie tens or hundreds of millions of years ahead. Are not late arrivals to an empty gathering. We are the very early ones, and the gathering itself has barely assembled. Whether that framing carries hope or isolation, probably depends on the moment you are in. What it does accomplish is a shift in the question from where is everybody to when is everybody, and in doing so, it strips the silence of its urgency. The galaxy may not be empty, it may simply be premature. But there exists a different category of civilization that might be out there right now, in this very moment, and that no telescope could locate. Not because they are hiding, not because they perished, but because they never developed anything we would recognize as a detectable signal at all. There is an assumption so thoroughly embedded in the search for extraterrestrial intelligence that it almost never gets examined. Intelligence leads to technology. That any species capable of abstract reasoning will eventually build machines, produce electromagnetic signals, and leave a traceable imprint on its environment. Earth's own history appears to support this, but Earth's history is a sample of one. Consider the cognitive sophistication of certain Earth species that never developed technology. Dolphins exhibit self-recognition, elaborate social structures, regional dialects, and problem-solving capacities that would have seemed extraordinary to researchers of an earlier era. Elephants mourn their dead, maintain multi-generational social memory, and cooperate in ways that imply genuine strategic reasoning. Crows and ravens fashion tools, plan for future contingencies, and recognize individual human faces, distinguishing allies from threats across years. Octopuses demonstrate problem-solving and learning behaviors that evolved entirely independently from vertebrate intelligence, suggesting that sophisticated cognition can emerge through radically different biological paths. None of these species are constructing radio transmitters. Intelligence and technological civilization are not identical. Intelligence is a cognitive property. Technological civilization is a specific cultural and biological trajectory that depends on a cluster of conditions that may not be universal. Fine motor manipulation, social structures supporting large-scale cooperation and knowledge transmission, sufficient environmental pressure to drive innovation rather than equilibrium, and metabolisms and lifespans that reward long-term investment in tools. Remove any one of those conditions, and you can have a planet full of intelligent beings, living rich, complex cognitive lives, while leaving essentially no signature detectable from space. An ocean world, for instance, could sustain vast populations of intelligent marine organisms with no access to fire, no capacity to work metal, and no route to electronics. Their intelligence might be profound. Their civilization by any internal standard might be ancient and sophisticated. From space, their world would appear as a featureless water body. This possibility scales uncomfortably. If even a significant fraction of planets with intelligent life host species that never develop detectable technology, the silence resolves without any filter, any catastrophe, or any concealment. The universe is dense with minds we simply cannot detect, because we are searching exclusively for the specific technological signatures our own trajectory produced. Some astrobiologists have begun taking this seriously enough to suggest that the definition of intelligence employed in the search for extraterrestrial intelligence is far too narrow. We are not searching for intelligence. We are searching for industrial civilization, and there is no guarantee that intelligence and industry travel together across every possible biosphere. This does not dissolve the deeper question. Even one civilization that developed technology in 4 billion years of Earth history managed to do so. Statistically, that should happen elsewhere. But the non-technological intelligence argument adds another layer to the silence. Some of what we are not hearing may not be silence at all. It may be a conversation conducted in a language we have never conceived. And the next layer of this idea runs deeper still, because even among species that do develop technology, the very architecture of their minds might render what they build or transmit unrecognizable to us. Over the past decade, the catalog of potentially habitable worlds in our own solar system has expanded dramatically, not through discoveries of Earth-like rocky planets with clear skies and thin atmospheres, but through something entirely different. Worlds with liquid water concealed beneath thick outer shells of ice, insulated from the cold of space by the weight of kilometers of frozen crust. These ocean worlds are now considered among the most promising candidates for life in our solar system, and potentially in the universe. Europa, one of Jupiter's moons, is estimated to harbor twice the volume of liquid water contained in all of Earth's oceans. It lies beneath an ice shell potentially dozens of kilometers thick, kept warm not by sunlight but by tidal flexing driven by Jupiter's immense gravitational influence. The seafloor may host hydrothermal vents comparable to those on Earth, where chemical energy rather than solar energy drives ecosystems in permanent darkness. Life exists around Earth's hydrothermal vents entirely independently of sunlight. This is confirmed. Enceladus, a moon of Saturn, actively jets plumes of water vapor and ice particles from its south polar region. Analysis by the Cassini spacecraft detected molecular hydrogen, silica, and organic compounds in those plumes, the chemical fingerprints of hydrothermal activity, and the raw materials of biology. Enceladus is actively venting material from its subsurface ocean into space. Whatever that ocean contains is already, in a sense, reaching us. Titan, also orbiting Saturn, presents a different kind of liquid environment. Dense hydrocarbon lakes on its surface suggest the possibility of chemistry-based life operating on entirely different principles from water-based biology. Titan's atmosphere is denser than Earth's and rich in organic molecules. Researchers have theorized metabolisms capable of operating in liquid methane rather than water. Now consider the Fermi implications. A civilization that evolved within a sealed subsurface ocean, beneath kilometers of ice, would face an almost insurmountable barrier to any form of space-based communication or exploration. They would have no access to the electromagnetic sky above them. No stars, no radio frequencies, no line of sight to anything beyond their world. Their entire observable universe would consist of the surrounding ocean and the rock beneath. Even if such a civilization developed intelligence, language, culture, and sophisticated technology adapted to their environment, the path toward radio transmission or space exploration would require them to first conceptualize that a universe existed above their ice ceiling, then physically penetrate kilometers of solid ice, then survive in a vacuum for which nothing in their biology or experience had prepared them. The obstacles are not purely engineering challenges, they are conceptual ones. A civilization that has never seen a star does not naturally arrive at the idea of broadcasting into space. Thousands of ocean worlds may exist throughout the galaxy right now, some harboring complex life, perhaps intelligent life, locked in silence beneath their shells, not silent by choice, but silent by architecture. This matters enormously for how we think about the Fermi Paradox. If a significant proportion of habitable environments in the universe are enclosed rather than open, the population of civilizations capable of electromagnetic communication is far smaller than the population of civilizations that actually exist. We are not simply searching for life, we are searching for a particular subset of life that happened to evolve in an environment compatible with the specific kind of curiosity that builds telescopes. But even among civilizations with access to open skies and the full electromagnetic spectrum, there may be a barrier as impenetrable as a kilometer of ice. A barrier composed not of rock or vacuum, but of thought itself. When we search for extraterrestrial intelligence, we are searching for something that resembles our own intelligence closely enough that we can identify it. Structured mathematical sequences, consistent frequency patterns, artifacts with geometric precision. The underlying assumption is that intelligence generates recognizable order. But that assumption has never been tested against any intelligence other than our own. Our entire concept of what constitutes a signal is built around what human minds produce. We search for prime number sequences because we would broadcast prime numbers. We flag anomalous geometric structures because we construct geometric structures. The entire search methodology is, at its core, a projection of human cognitive style onto a universe we have never actually surveyed for cognitive diversity. Consider what a genuinely alien intelligence might look like. Not one that shares our evolutionary pressures, our sensory apparatus, our social arrangements, or our experience of time, but something that developed under fundamentally different constraints, on a fundamentally different world, perhaps one with multiple simultaneous processing streams, rather than a single linear thread of consciousness, or a relationship to information storage and retrieval that operates across a biological substrate, nothing like our nervous system. There is no guarantee that such an intelligence would produce anything we would identify as structured communication. Its artifacts might register in our instruments as natural noise. Its signals might carry information in dimensions we do not monitor. Its technology might operate on physical principles we understand theoretically, but have never observed being applied. We might look directly at the evidence and perceive nothing, not because nothing is there, but because we lack the cognitive or instrumental framework to parse it. Researchers studying animal cognition have encountered modest versions of this problem right here on Earth. For decades, non-human communication systems were evaluated against whether they resembled human language. Species that failed that test were classified as non-linguistic. As researchers developed new analytical frameworks, previously invisible complexity surfaced. Prairie dog calls have been shown to encode surprisingly detailed information about predator characteristics. Whale song carries structural features that share mathematical properties with human language. Bee dances communicate distance and direction through a physical medium no human sensory system can read directly. These are animals sharing billions of years of evolutionary history with us. An alien intelligence sharing none of that history might be so fundamentally different in cognitive architecture that the gap is not a translation problem but a categorical one. The instruments we build to listen are calibrated to patterns our minds can process. Patterns our minds cannot process pass invisibly through those instruments. This is a genuinely sobering point. The Fermi Paradox may not be posing the right question. The question is not where is everyone? It may be whether we could identify everyone even if they were in some meaningful sense present. The silence might represent a communication breakdown at the most fundamental possible level, not a failure to transmit, but a failure to perceive. And if that cognitive barrier applies to what we can receive, it applies equally to what we send. Any message we broadcast is constructed to the specifications of a human mind. Whether it carries any meaning for a radically different kind of intelligence is a question we cannot answer from inside our own cognition. This leads to one of the most unsettling ideas on this list. Not that intelligence lurks out there in hiding, not that it arose and perished, but that it may have reached us long ago and left something behind. Something we have been looking at for billions of years without recognizing what it is. In 1973, Molecular biologist Francis Crick, who shared the Nobel Prize for co-discovering the structure of DNA, co-authored a scientific paper with astronomer Leslie Orgel proposing something the scientific establishment received with considerable skepticism. Their hypothesis, which they named directed panspermia, suggested that life on Earth did not originate here through purely natural chemistry. It was deliberately seeded by an extraterrestrial civilization. Crick arrived at this not through mysticism, but through biochemistry. He was troubled by what he regarded as the extreme improbability of life generating spontaneously from raw chemistry within the available time window on early Earth. Life appeared remarkably quickly after Earth's surface cooled. The genetic code is also extraordinarily universal, a single coding system shared by every known form of life on Earth, from bacteria to redwood trees to humans. Crick found this universality suspicious. It implied either a single common origin or deliberate design using a standardized system. Directed panspermia proposes that a sufficiently advanced civilization confronting the eventual death of its star or other existential threats might have seeded numerous worlds across the galaxy, with microbial life or its chemical precursors, not to colonize, not to communicate, but simply to propagate biology as broadly as possible, ensuring that wherever conditions eventually became favorable, life would begin. If this hypothesis holds, it fundamentally reframes the Fermi Paradox. The origin of life on Earth might not be an independent data point at all. It might be evidence of a prior civilization that no longer exists in any form we recognize. The silence we observe would be the silence of a forerunner, a civilization that may have peaked billions of years ago, seeded what it could, and then vanished. The hypothesis is by its nature almost impossible to confirm or falsify. The genetic code's universality can be explained by common descent from a single ancestral population, which is the scientific consensus. The speed of life's appearance on early Earth, while striking, has proposed natural explanations that Crick's critics found adequate. What the hypothesis productively accomplishes is forcing a different kind of question about the search for life. If panspermia, directed or natural, is a real mechanism, then finding life elsewhere in the galaxy would not necessarily confirm an independent origin. Two life-bearing worlds might share a common biological ancestry, either through natural transfer of material between star systems during early solar system formation, or through deliberate seeding by a civilization of which we have no other evidence. A recent research direction supports at least the natural version of this idea. Rocks ejected from planetary systems during formation can journey between stars across millions of years, occasionally arriving on new worlds. If those rocks carry dormant microbial life, which some research suggests is physically feasible, then life could propagate across star systems without any civilization's intervention. The directed version adds only intent to a mechanism that may already operate naturally. Whether or not any civilization deliberately seeded the galaxy with life, the question of our own origins may be less settled than biology textbooks suggest. The precise mechanism by which chemistry became biology on Earth remains, as of today, an open scientific question. Crick's hypothesis stands at the edge of that opening. And if we were placed here intentionally, the civilization responsible may have left behind more than just life. Some researchers have begun asking whether the answer to the Fermi paradox might require no telescope at all, only a much closer examination of something already in our possession. In 2001, philosopher Stephen Webb formulated a hypothesis occupying a strange position between the simulation argument and something simultaneously more specific, and, in certain ways, more disturbing. He called it the planetarium hypothesis. The idea is not that we inhabit a fully simulated universe. It is that the cosmos visible to us has been deliberately engineered to appear empty, a kind of cosmic stage production designed to isolate us from the reality of what the universe actually contains. The premise begins with a straightforward observation. Every piece of information we possess about the universe beyond our solar system arrives via electromagnetic radiation, light, radio waves, X-rays, gravitational waves. Every distant star, galaxy, and cosmic structure we have mapped is known to us only through signals that have traveled to our instruments. We have never directly visited anything beyond our immediate cosmic vicinity. Our entire picture of the universe is assembled from what reaches us here. This creates a vulnerability. A sufficiently advanced civilization wishing to construct a false impression of an empty universe would not need to alter the actual universe. It would need only to manage the signals arriving at our solar system. If such a civilization could intercept or overlay the electromagnetic information reaching Earth, replacing the signatures of inhabited worlds and alien megastructures with empty, static, or naturally appearing noise, we would have no means of knowing. The planetarium hypothesis is, in one reading, a sophisticated extension of the zoo hypothesis. Under the zoo model, civilizations simply remain quiet. Under the planetarium model, they actively maintain an illusion of vacancy, managing what we observe so comprehensively that our most powerful telescopes find nothing, because they have been arranged from the outside to find nothing. This hypothesis is not testable with any current instrument, its most significant scientific limitation. An illusion crafted by a sufficiently advanced civilization to be undetectable would by definition be undetectable to us. Every observation we make could fall within the managed zone. Every anomaly we classify as natural could be a seam in the fabrication. This renders the planetarium hypothesis less a scientific proposition than a boundary condition on scientific epistemology. It marks the edge of what can be known from inside the system being analyzed. If the inputs to our analysis are controlled, our outputs are meaningless. That is a genuinely uncomfortable position for science to inhabit. What the hypothesis shares with other advanced civilization solutions to Fermi is the implication that the silence is intentional, not a product of rarity, destruction, or distance, but of deliberate management. The universe looks empty because something wants it to look empty. Whether that something is benevolent, curious, cautious, or indifferent to our perception of reality is a question the hypothesis offers no framework for answering. A different version of this idea requires no active deception at all, only that the observable universe, the portion accessible to our instruments given the speed of light and the cosmos's age, is simply too limited a sample to contain evidence of intelligence that exists beyond it. The universe may be vastly larger than what we can observe. Other civilizations may exist at distances so extreme that their light has never had time to reach us since they formed. The silence of our observable bubble is not the silence of the universe. It is the silence of our corner of it. Either way, we are working with incomplete information, and the most haunting question may be whether that incompleteness is accidental or deliberately arranged. What follows is not philosophy. It is biology, and it may hold the most personal version of the Fermi answer yet. For decades, the search for life beyond Earth operated almost entirely in the domain of theory. Researchers built models, ran simulations, and debated probabilities while actual observational data remained frustratingly sparse. That situation has begun to shift, and the shift is significant enough that some researchers describe this decade as the opening of a genuinely new era in astrobiology. The James Webb Space Telescope, launched in late 2200 and fully operational by 2002, has given astronomers the ability to analyze the atmospheric composition of exoplanets with a precision previously unattainable. When a planet transits its host star, a fraction of starlight filters through the planet's atmosphere before reaching our instruments. Different molecules absorb light at characteristic wavelengths. By analyzing which wavelengths are missing from that filtered light, researchers can identify atmospheric compounds from thousands of light years away. In 2023, a team using James Webb announced the detection of carbon dioxide and sulfur dioxide in the atmosphere of a planet designated K2, 18b, a world roughly 2.5 times Earth's diameter, orbiting in the habitable zone of a cool star approximately 120 light-years away. Sulfur dioxide can be generated by photochemical reactions involving biological molecules in ocean water under certain conditions. The research team described this finding as tentative and requiring follow-up confirmation. It was not presented as proof of life. Then, in 2025, the same team published results announcing the apparent detection of dimethyl sulfide in the same planetary atmosphere. On Earth, dimethyl sulfide is produced almost exclusively by marine phytoplankton. No confirmed abiotic pathway exists for generating it at the concentrations the data implied. The signal was described as exceeding 3 sigma in statistical significance, strong enough to take seriously, but not yet meeting the 5 sigma threshold conventionally required for a confirmed discovery in physics or astronomy. The scientific community responded with both genuine excitement and measured caution. Multiple independent researchers raised questions about the statistical interpretation and the difficulty of distinguishing weak signals from instrument artifacts at these distances. The detection has not been refuted. It has not been confirmed. It is currently undergoing ongoing analysis and debate, precisely as the scientific process demands. What this represents, regardless of the final verdict on K2, 18b, is a proof of concept. The instruments now exist to detect biologically relevant atmospheric chemistry on distant worlds. Within this decade, with continued James Webb observations and the eventual deployment of next-generation telescopes currently under development, researchers anticipate, having analyzed the atmospheres of dozens of habitable zone planets, with sufficient resolution to begin constructing a statistical picture. If multiple independent worlds display atmospheric signatures inconsistent with purely abiotic chemistry, the case for widespread life becomes very difficult to argue against. If every habitable world we examine shows only chemical equilibrium with no biological perturbation, the case for the rare earth hypothesis or the great filter strengthens considerably. The answer to the Fermi Paradox may, for the first time in history, be within the reach of instruments we have already built. But if we do find evidence of life elsewhere, a different and deeply human challenge immediately arises, one that researchers are already debating with unusual intensity. The search for extraterrestrial intelligence is, by its historical design, passive. We listen, we scan, we catalog anomalies. We have not, as a civilization, made any systematic decision to actively and powerfully broadcast our presence into the cosmos. That is beginning to change, and the scientific community is deeply divided about whether that change is prudent. METI stands for Messaging Extraterrestrial Intelligence. Unlike passive listening programs, METI involves deliberately transmitting powerful targeted signals towards specific stellar systems in the hope of initiating contact. The logic is straightforward. If every civilization waits for someone else to transmit first, no one ever makes contact. Someone must go first. The counter-argument is equally direct. We do not know who is listening. We do not know their intentions. We do not know their capabilities relative to ours. Announcing our location and technological level to an unknown audience carries risks that cannot be quantified, and risks that cannot be quantified cannot be managed. Stephen Hawking stated publicly before his death that attempting to contact extraterrestrial civilizations was, in his assessment, dangerous. He drew the analogy to historical contact between technologically unequal civilizations on Earth, where the outcome for the less advanced was consistently catastrophic. He was not alone. A significant number of researchers in astrobiology, astrophysics, and existential risk have argued that active messaging should require global consensus before proceeding. Given that any response to a transmitted signal would arrive after a delay of decades to centuries and would affect all of humanity, not merely those who sent it. Others argue the opposite. If the dark forest scenario is real, we are already detectable. A century of broadcast radio and television signals has generated an expanding electromagnetic bubble already exceeding 100 light-years in radius. Any civilization within that range already knows we exist. Silence now cannot undo that. If we are already visible, the practical force of remaining quiet is limited. The debate also touches governance questions that science alone cannot resolve. Who holds the authority to speak for Earth? No international treaty currently governs METI. Individual observatories and private organizations can, in principle, transmit whatever they wish. Several powerful targeted transmissions have already been sent without any global consultation, including a high-powered broadcast toward a stellar system in 2008. What elevates the METI debate beyond academic exercise is timing. The development of high-powered phased array transmitters and advances in targeting precision now make it technically feasible to send signals detectable at stellar distances. The capability exists. The will exists in at least some quarters. What does not exist is consensus, protocol, or governance. The question of whether to call out into the dark, knowing nothing about what might answer, or to hold silent in a universe that may already have heard us, stands as one of the first genuinely civilization-scale decisions humanity faces in the domain of space. It may be the most consequential choice we make this century, with consequences that neither we nor our grandchildren will live to see fully resolved. But the most unsettling dimension of the Fermi Paradox may involve nothing we transmit outward. It may involve something present since the very beginning. There is a version of the Fermi answer requiring no telescope, no signal, no distant world. Only a careful examination of ourselves, our DNA, our biochemistry, and the specific molecular record inscribed in every cell of every organism on Earth. The idea begins with a genuine scientific puzzle. The genetic code is universal. Every known form of life on Earth, every bacterium, every plant, every animal, uses the same basic system to translate DNA into proteins. The code maps specific triplets of chemical bases onto specific amino acids. This mapping is essentially identical across all life. Standard evolutionary theory explains this universality through common descent, all life descending from a single ancestral population. That is the scientific consensus. But some researchers have pressed a harder question. Why this particular code? Among the astronomically large number of possible mappings between base triplets and amino acids, The specific code employed by all life on Earth appears remarkably optimized. Studies have shown it is extraordinarily resistant to mutational errors, that single-base mistakes produce minimal changes in protein function compared to most random alternative codes. The probability of arriving at a code this optimized through purely random initial assignment is, by some mathematical analyses, extremely low. This could mean the code was refined through early evolutionary pressure before the last universal common ancestor, operating during a period from which we have almost no direct fossil record. That is the mainstream scientific position. In a more speculative framing, it could mean the code was designed. Physicist Paul Davies has written about what he describes as the possibility of a cosmic legacy. The idea that a sufficiently advanced civilization might encode information into the genome of a biological organism seeded across the galaxy, not as communication in any conventional sense, but as an archive. NA is extraordinarily information-dense and extraordinarily stable under the right conditions. A message embedded in the non-coding regions of DNA, the roughly 98% of the human genome that does not directly code for proteins, could theoretically persist for billions of years. This concept has migrated from pure speculation into, at minimum, scientific curiosity. Researchers have begun systematically examining genomic data for mathematical structures or information patterns inconsistent with purely evolutionary origin. No confirmed finding has emerged, but the methodology is new and the analysis continues. There is also a simpler biological version of this idea that requires no encoded messages. If life on Earth was seeded from another world, whether intentionally or through natural interstellar transport, then our biology itself constitutes evidence of life's presence elsewhere in the cosmos. Every cell in your body may carry the chemical signature of an origin that began somewhere other than Earth. Not metaphorically, physically, whether our biology is a record of this planet's own chemistry, or a letter dispatched from somewhere far beyond, the answer to the Fermi Paradox may have resided inside us all along, not in our technology, not in our telescopes, but in the molecule that defines every living thing we have ever found. We have been searching the sky for signals. The deepest signal may be the one we are built from. Every theory we have explored offers a different answer. Some suggest the universe teems with life too simple to signal. Some suggest civilizations arise and extinguish themselves before reaching out. Some suggest intelligence is so rare we may be the only minds ever to have formed in this region of reality. Some suggest the silence is managed, temporal, or a reflection of our own perceptual limits. We do not know which is true. That uncertainty is not a failure of science. It is the honest frontier of what any civilization can know at our current stage of development. But consider the most stark possibility, that the silence is genuine, that it is permanent, that no other technological civilizations exist in this galaxy, that none have sent probes or signals or artifacts we can detect, and that the reason is some combination of everything we have examined. Life is uncommon, complexity is rarer. Intelligence is rarer still, and the civilizations that do emerge tend to be fleeting, separated by distances in space and time that cannot be bridged. If that is true, what does it mean? First, it transforms our sense of responsibility. If we are the only minds in this galaxy capable of asking these questions, of examining the cosmos and understanding what it is, then our survival is not merely a human matter. It becomes a cosmic one. The universe has, through us, produced something capable of observing it, understanding it, and potentially shaping parts of it. If we erase ourselves, that capacity vanishes with us. There is no fallback, no second opportunity from a neighboring civilization waiting to carry the work forward. Second, it recontextualizes everything we build. Every piece of knowledge we accumulate, every scientific achievement, every cultural creation exists in a context where it may be the only such thing in the galaxy. Not the finest version of something common, the only version of something rare. That does not shrink our problems or make our conflicts less real, but it adds a dimension to their stakes that the Fermi Paradox makes impossible to ignore. Third, it reframes exploration. If the galaxy is largely vacant, the long and difficult project of becoming an interstellar civilization is not the act of joining a populated cosmos. It is the act of filling one. Every world we eventually reach, every system we study and perhaps one day inhabit, we would arrive at as the first mind ever to encounter it. The strangeness and weight of that firstness is difficult to hold fully in the mind. Fourth, and most urgently for this present moment, it gives pressing meaning to the question of whether we survive our own critical phase. The century we inhabit is widely recognized by existential risk researchers as one of the most consequential in our species' history. Artificial intelligence, biotechnology, climate disruption, and the geopolitical pressures that accompany rapid technological change are converging within a window that, by cosmic standards, is instantaneously brief. Whether we navigate it successfully matters enormously if we are alone. It matters even more if our survival might one day answer the question for some other species, millions of years hence, that turns its instruments toward the sky and wonders whether it is the only one. We began this journey with a simple question: where is everybody? We have moved through layer after layer of possible answers and arrived not at a single clean resolution, but at a portrait of a universe that is, in every direction, asking something back. Whether life is abundant or rare, whether the filter lies behind us or ahead, whether the silence is natural or orchestrated, the silence itself carries a message. It tells us that whatever we are not ordinary, and whatever comes next, we are the ones who choose it. The universe is watching, or it is not. Either way, the choice of what to do with that uncertainty falls entirely to us, in the narrow, fleeting, extraordinary window of time we have been given to make it. We may be the first minds in this galaxy to have reached this point. We may be the only ones who ever will. The responsibility that comes with that, to endure, to understand, to reach, may be the most profound inheritance any species has ever received, and what we do with it in the years and centuries ahead will either justify that inheritance or mark its end. The sky is silent, but we are not yet.